Remember when we ground through all that messy algebra for x squared using the first principle's limit definition? I promise you right here, right now, we derive one shortcut rule that will let you skip that grind forever. Let's earn it properly, just once, with full working shown. Here is our starting point, the first principle's definition of the derivative. Derivative of f of x equals limit, as h goes to 0, of, open bracket, f of x plus h minus f of x, close bracket, divided by h. Let's take f of x equals x cubed first, since we can expand it by hand. On screen, in 2D, we show the curve y equals x cubed with a secant line through x and x plus h. Alongside it, in 3D, we tilt the same curve into a surface-style view, so you can see the same secant construction from another angle, with all labels kept flat and horizontal. We need, open bracket, x plus h, close bracket, cubed. Using the binomial expansion, this equals x cubed plus 3x squared h plus 3xh squared plus h cubed. Now subtract x cubed, since the definition needs f of x plus h minus f of x. That leaves 3x squared h plus 3xh squared plus h cubed. Notice the plain x cubed term has cancelled completely. Divide everything by h. We get 3x squared plus 3xh plus h squared. Every remaining term still has at least one factor of h in it, except the very first one. Now take the limit as h goes to 0. The term 3xh goes to 0, and the term h squared also goes to 0. Only 3x squared survives, so derivative of x cubed equals 3x squared. Before we generalize, pause the video for a second. Look at that result, 3x squared, and think back to the pattern. Can you predict what derivative of x to the n would be for any whole number n based on just this one example? Let's check your guess using n equals 4. Open bracket, x plus h, close bracket, to the 4 equals x to the 4 plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the 4. Subtract x to the 4, divide by h, and take the limit as h goes to 0. Every surviving term except 4x cubed h divided by h dies off, leaving derivative of x to the 4 equals 4x cubed. Do you see the pattern now? In both cases, the surviving term was exactly n times x to the n minus 1 times h, and dividing by h left n times x to the n minus 1 behind. Let's generalize this properly for any positive integer n, using the full binomial expansion. Open bracket, x plus h, close bracket, to the n equals x to the n, plus nx to the n minus 1, h plus sum from k equals 2 to n, of the binomial coefficient n choose k, times x to the n minus k, times h to the k, subtract x to the n. The plain x to the n term cancels, leaving nx to the n minus 1, h, plus that whole sum starting from k equals 2, which we know only contains terms with h squared or higher powers of h. Now divide by h, we get nx to the n minus 1 plus sum from k equals 2 to n, of the binomial coefficient n choose k, times x to the n minus k, times h to the k minus 1. Every term in that remaining sum still carries at least one positive power of h, since k minus 1 is at least 1. Take the limit as h goes to 0. Every term in that sum vanishes, because each one is a fixed number times a positive power of h. Only the first term survives, giving us derivative of x to the n equals nx to the n minus 1. That is the power rule derived once and for all. Let's sanity check this against the previous video. There we ground through the limit definition for f of x equals x squared and got derivative equals 2x. Plugging n equals 2 into our new rule gives nx to the n minus 1 equals 2x to the 1 equals 2x. It matches exactly, so our general formula is consistent with the hard work we already did. If this saved you from ever grinding through that binomial algebra again, hit like and subscribe. It genuinely helps. Next video, we take this power rule and combine it with a brand new tool, the product rule, so we can differentiate products of functions like x squared times sine of x. See you there.